Okay, welcome back to the second part of today's lecture. So my laptop stopped without any warning. So we stop here at this slide as far as I can remember. Okay, so let's continue this slide. Okay, so we talk about the quantization voltage. So this is or value. So this is the last term under quantization. See? That you were introduced to. So in this example, where our quantized voltage of the lowest level is equal to minus 4.375, okay, so it says here that sample in this level 0 segment is represented by bit 000, and the quantized voltage for this level is minus 4.375. So what I've mentioned in the previous video is that even though our sample, for example, is minus 5, but it will be rounded to minus 4.375 because a quantization will round our sample value to the nearest quantized value. So the difference between the actual sampled value and the quantized value is known as the quantization noise or quantization error. Okay. So that's it for some terms, introduction to PCM. And in our next slide, okay, we look at the first PCM type based on the quantization, which is uniform quantization. And here is the conventional, or known as the non-folded. Okay, so this type of PCM is also known as non-folded or just normal quantization. So non-folded or normal. So this is the most conventional, the basic uniform quantization type. Okay, if you look at this example, again, we just use the same values for our parameters of n equal to 3, L equal to 8, signal, V peak to peak 10 volt, and delta V is 1.25 volt. So our we have 8 levels starting from level 0 to level 7. So this is basically the decimal value of our binary codes. So with 3 bits, the combinations that we have is from 000 up to 111. So 000 level 0, 001 level 1, and the last one 111 is for level 7. So these are the levels and codes for that specific levels. Okay, and when we calculated, remember we calculated our VKL, which is the value, quantized value for the lowest voltage. So it's this one, minus 4.375. So this is our VKL, yeah. So lowest quantization voltage. Up here, the highest voltage is where we have VKH. Okay, so we calculated our VKL and we got minus 4.375. And for the above levels, we just add delta V at 1.25. So you add minus 4.375 with 1.25, you get the value for the next, which is minus 3.125, and then just for add some more, so on and so on. So we should get for the highest levels is 4.375. Okay? So either way, if you add from top to be up, if you add from bottom to top, or you just use formula VKH equal to Vmax minus delta V over 2, you should be able to get the same answer. Okay, let's try with VKH equal to 5 minus 1.25 divided by 2. So if you solve this, 1.25 divided by 2 is 0.625. Okay. So you get the same answer, 4.375. So that's why I say either way, whether you use formula right away or you add from bottom until to the highest level by delta V, you should get the same value, 4.375. Okay, so these are the sampled voltages, these black fonts, 1.9, 4.3, and so on. So these are the sampled voltages, the actual voltage from our information analog signal. Okay, so if you look here, 1.9, what is the quantized voltage? After quantization, this will be 1.875. If you round it to 1.875, this 4.3 also will be rounded to 4.375. The same thing. So difference between them is known as quantization error or quantization noise. Okay. Okay. Another thing that I want to introduce is bit rate. So for digital communication, our bit rate is NFS. Okay, where N is the number of bits and Fs is our sampling frequency. Okay, so this Fs should be larger or equal to 2 FM, and then so this will determine number of samples that we have. So number of samples, and this is number of bits per sample. N is number of bits per sample, and this part determine number of samples that we have. So how we got our bit rate, number of bits per second that transmitted. Oh. Okay. So the next one is folded binary code. So then the previous one that I explained is the non-folded binary code, or the just normal uniform quantization. There's another type of uniform quantization known as folded binary code. So the main difference here is that we have a sign bit at the beginning of our code. So this most significant bit, MSB, over here represent our sign bits. Okay, so in this example, this was the example of a folded binary code. So this MSB, bit 1 is for positive voltage, bit 0 negative voltage, and so by just looking at our codes, we'll know that okay, this is negative. We can differentiate easier. This negative, this positive voltage, and so on. But intervals, the difference between levels is still the same, which is delta V. It's just that how we assign codes to the levels that differentiate between the previous and this technique. Okay, so this shows how we convert quantize to PCM codes. Okay, like for example here, the level is 100. Okay, so remember that quantize level, we take the middle voltage. So here, the red line is red, and the red squares. This are the our quantized voltage. This pulses black with black font is our sampled. So difference is quantization error. So for the first sample, it will be converted to 100, and the second one nearest is 101, third 111. So that's how it converted from quantized voltage to PCM codes. Okay. That's okay. So the quantization error is also known as quantization noise. So the maximum quantization error is half of our interval. Okay. So the maximum quantization error is delta V over 2. Okay. Let's move to the next. So this slide illustrates the effects of quantization error in our signal. Okay, so this is our original information signal, which as you can see it's analog. Okay, and then we sample our signals. So we just take value at specific intervals at t, 2t, 3t, 4t, and so on. Okay, so and then after that, after sampling, we quantized, and here we round our sample to quantized voltage. So there will be difference between them. And at the receiver will receive only the quantized voltage. Okay. So if you notice, there will be slight difference between the original and the recovered. So the differences is due to the difference between quantized voltage and sample voltage. So it's known as quantization noise. And in order to reduce the difference, what you can do, one of the strategy is by increase the number of levels. When we increase number of levels, meaning the resolution will be finer, then our quantized voltage can represent our sample voltage better, and subsequently this lead to lower quantization error or quantization noise. But there is also a trade-off. We cannot just simply increase our quantized PCM bits, because when we increase n high, what will happen is that our FB also will be high because it's directly related, and FS. So if you use higher n, even though it will be more accurate, but the bit rate will be higher. Okay, so there is a trade-off. We want accurate, reliable system, but at the same time, we don't want to use so much resources. Okay, because FB is related to bandwidth. We don't want to utilize a lot of bandwidth in our spectrum. Okay, let's move to the next. Okay, so for VCM, we have this term as SNRQ, which is SNR due to quantization error. And for uniform quantization, the formula is 1.76 plus 6.02n. Okay, so n is the number of bits. Okay, so n is number of bits, and you just multiply n with 6.02, and all this, the answer is in dB. Yeah, so you have to be careful. The whole thing is in dB. So noise from quantization error can be reduced by increasing n, which is the number of bits. Like I said, but there's a trade-off between bandwidth and error. Okay, let's look at some formula. Okay, so this formula, we have formulas for folded and non-folded and folded uniform quantization. We have this formula. You can actually do it manually like before, but if our n is high, then it will be very time consuming. Yeah? If we want to determine what are the codes for certain voltage, or when you were given voltage, what is the codes for that voltage. Okay, so this for this situation, if you use formula, that can be helpful to solve the solution, to solve a problem. So we have in our formula, x is the decimal value of binary code, VKL is the lowest level of our quantized voltage. So when you're given a binary code, and you want to know what's the quantized voltage for that specific code, okay, you can use this formula. It's VKL plus the decimal value of the code. If we convert from binary to decimal, and the decimal value for that code multiplies with our quantization interval, then plus VKL. So then we get the quantized voltage for that binary code. And when you're given voltage, to find the code to the binary code, we just rearrange the equation, put x at the front, which is equal to voltage minus VKL divided by delta V. When you got x, which is the decimal value, we convert x to binary. Okay, so these are the formulas. They will be given in the exams. Yeah. So this is especially useful if we have high number of bits. So it's very troublesome and can be, we tend to make mistakes, careless mistakes, if we need to sketch all the quantized voltages, levels, and values if we have high number of n. Okay, let's look at this one example. Okay, in this example, our bit is 7 and our voltage is between plus and minus 16 to plus 16 volt. So the V peak to peak is 32. What is the first number of levels? And then the delta V, also known as LSB voltage. Maximum quantization noise, the voltage value for 110, 1101, and voltage value for 001, 1001. And then you're given voltage, you need to find what are the codes for that voltage. So you have two voltage values, plus 13.62 and minus 9.37. Okay, so let's solve this in our next part. I'll just stop here so it won't be too long on the video.